Welcome. I'm Professor Lloyd, and I'm going to talk to you today about the qualitative analysis experiment. This is going to be qualitative analysis part 1 and part 2, the group 1 ions. Now, the group 1 ions that we're going to look at today are the ammonium ion, NH4+, the silver ion, Ag+, the copper 2 ion, Cu2+, and the bismuth 3 ion, Bi3+. In a subsequent experiment, we'll look at the group 2 ions, manganese, nickel, iron, aluminum, and zinc. So what we're going to do is we're going to use several different standard methods of analysis in chemistry to separate chemically the ions by using their specific reactivities and then using physical processes such as centrifugation in order to actually physically separate them so that we can analyze them. So the methodology here, the introduction and the methods are shown on our board here. So let me scroll down a little bit so you can see the discussion. This gives you some background information. This is a way that you could take notes during the experiment. I'll leave it to you to do that for yourself. We would number the steps that we're going to do. We would indicate what material we're going to work with, what reagent, what chemical we're adding to the material. If a reaction or some process occurs, what is the color of the solid that is formed? That's the precipitate. If we separate the solid from the liquid called the supernatant, the solution might have a color, we would indicate that. And if there is a chemical reaction occurring during that process, we would indicate that as well. That equation is actually the first equation in this whole process. Now there is, as you read through the procedure, some details in terms of how you might write down the information as you go along, and some details about the materials that we're using. In this video lecture, you will see how it's done as me as your demonstrator. So parts 1 and 2, the separation and conformation of the group 1 ions, ammonium, silver, copper, and bismuth, we're going to use this procedure that's indicated here starting on page 3. What it says is, in the first step, you're going to place 15 drops of the group 1 solution into one centrifuge tube and 5 drops in another centrifuge tube, and then you're going to make sure that you don't get any of the solution on the lips of the containers. So over here, this is our workstation. Right here what we have are the centrifuge test tubes, which are plastic tubes. We also have reagents. The reagents are over here, as are our group solutions, and we have pH paper, which I'll discuss in a few moments. We have boiling water here, which we'll need in order to get the reaction started. We also have a centrifuge, which we will use to separate the supernatant from the precipitate. So what we're going to do is we're going to take that first step that we have there. We're going to take 15 drops of the group 1 known solution. That's right here. Notice it has a greenish tint to it. And we're going to add 15 drops of that into this tube. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's 15 drops into one of these tubes. Notice that when I dropped it, I paid special attention not to get the drops on the lip. If I were to get them on the lip, I would wipe that off as well as I could. I'm going to put that test tube here. Into another tube, I'm going to drop 5 drops of the group 1 solution. So here's 1, 2, 3, 4, and 5. There we go. Okay. It's always good chemical hygiene to close the screw caps as well as you can after you've used it. Now over here, I have the unknown solution. So what I'm going to do is I'm going to take this unknown, which is number 10B. And we're going to analyze this unknown at the same time, or essentially the same time, as we analyze the known. This solution might have all 4 ions in it, or it might only have 3 or 2. We're not sure. We're going to use our analysis of the known and compare it to the unknown to figure out which ions are actually in this solution. So, same idea. We're going to take 15 drops. I'm going to use this little transfer pipette here, and I'm going to put 15 drops into the first test tube. And then I'm going to take 5 drops and put them into the second. Okay. All right, there we have that. We're going to analyze both of these. So I'm going to move these 2 test tubes up here so that we know what we have. Okay, so now we're ready for what's called the conformation of ammonium, NH4+. So it says here, to the test tube that has 5 drops of the group 1 solution, you're going to add 10 drops of 3 molar sodium hydroxide, NaOH, being very careful not to get any of the solution on the mouth of the tube. And you're going to place a piece of wet pH indicator paper on the top of the tube and then heat the tube into boiling water. Now, the idea here is that ammonium is a weak acid. If you add sodium hydroxide, it will convert the ammonium into a weak base called ammonia, NH3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There we go. Look at, there is a precipitate that has formed. You can see this greenish, grayish solution. And what I'm going to do is I'm going to stir it. Now we have a couple different ways we could stir it. One is using the vortex mixer. So let me show you the vortex mixer. I'm just going to place this on the side and it will mix it really, really well. That's one way to do it. Another more old-fashioned way, sometimes works very well, is just to use a glass stirring rod. Either way is a perfectly fine method in order to mix that up. Okay? Now I'm going to come over here and rinse this off because it now has some of that group 1 solution on it. There we go. A little Chem wipe to clean that up. Okay, now I'm going to take a piece of wet filter paper. Now when it says wet, we generally want to use distilled water. That will allow the dye that is embedded on the paper to be able to undergo a reaction. Solids generally react very slowly, liquids more rapidly, so we're making it a liquid there. Now what I'm going to do is I'm going to place this in our hot water bath. Pay close attention to the pH paper. If it turns green, that means that it's being exposed to a base. Ammonia, NH3, is a weak base. It's also a gas. So heating this liquid up will cause the gas to move through the air, to interact with the dye molecules on this pH paper, and change that paper green. You can see it working very nicely, right? Right there, that tells you that ammonia is being produced inside that test tube. The ammonia is coming from the reaction between sodium hydroxide and the ammonium ion. That's a definite positive result right there. We definitely have ammonium working. Now, what I'm going to do is I'm going to do exactly the same thing over here. I'm going to take the one that has 5 drops and I'm going to add 10 drops of the sodium hydroxide. Again, we want to check our labels. Sodium hydroxide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little bit more than 10. Notice there it looks quite a bit different than the last time. Before, it was a darker greenish. Now, there's two reasons that might be. One is maybe I didn't drop exactly the same amount of sodium hydroxide, so it could be it's off a little bit. Or it could be that it has a different composition. Maybe some of those ions that were in the known are not in here. So here's what I'm going to do. To resolve the issue of whether maybe I didn't add enough of the sodium hydroxide, I'm going to stir it, and then I'm going to test the acidity on this paper. So it turns a dark blue. That means it's very basic solution. This solution is basic, which means I added enough sodium hydroxide. So if it looks quite a bit different from the known, that means there's a different composition in here. We don't know what that difference is yet, but we're going to try to figure it out. So again, I'll come back over here, rinse this off, wipe it, and then put it back into there. We'll do exactly the same test. So the test says that we take some distilled water, wet this, put it over the lip, and then test to see whether we get the change of that dye that's embedded in the pH paper to see whether that turns green or not. If it turns green, that means there was ammonium in that solution. If it doesn't turn green, that means there wasn't ammonium. So we'll give it a minute just to see whether it changes color. Okay. Now I'm looking at it, staring at it. I'm starting to see a little bit of greenish color occurring in the middle there. So I'm going to give it a few more seconds to see whether that's true, and it looks like it is. If you take a look at that paper, it's turning green just like it did with the known, right? So that tells us that there's ammonia being produced, which tells us the sodium hydroxide must have reacted with the ammonium to produce that ammonia. This is a positive test. It wouldn't change to that color if there hadn't been ammonium in the solution. So we have a positive test. We have a positive result. I'm going to go ahead and move these over to the right. And now I'm going to come back over to our board. I have a little table here. The table here has all 4 ions, and we're going to indicate whether we get a positive or negative. For the known, we should have a positive every time. Notice for the copper, there's 2 tests. For the unknown, we're not sure. So we're going to go ahead and figure it out. We got a positive for the ammonium for the known, for sure. And we also got a positive for the ammonium for the unknown. We now know the identities of one of the ions in that solution. Now we're ready for part B. This is the separation and conformation of the bismuth 3 ion. The bismuth 3 ion will require some chemistry, which is discussed in this procedure, some chemistry involving the ammonia complex of silver and copper, and how bismuth does not behave the same way. So what it says to do here is to take the test tube that has the 15 drops of the ions that we're interested in. We're then going to add 15 drops of ammonium hydroxide, NH4OH. I'm going to close that completely. Here's ammonium hydroxide. That's what we're going to add. Ammonium hydroxide is a base. And so we're going to add this base. It's a weak base. We're going to add 15 drops of it to the centrifuge. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Notice definitely something happened. I'll bring it over to the vortex mixer. Let's mix this solution up. There we go. That looks pretty good. We got a mixed up solution. But again, I added a base, so this should now be basic. So let's test using the pH paper to determine whether I added enough in order to make this solution basic. So I'm going to take a drop, mix it over here, take a look at what happened to the paper. See how it turned that dark green? The dark green litmus paper, or pH paper more technically, that indicates that this is basic, which means that this solution that we put the drop on must be basic as well. That's what we expect it to be. Okay? So now what I'm going to do is just rinse this here a little bit. And now we're going to come up to the next step. The next step says to add enough to make sure that it's precipitated, add 2 more drops. So we're really just going to make sure that we added enough. 1, 2, and then stir. We know we definitely added enough right now. Now, once we've done that, we're going to stir, centrifuge, and decant, pour off the supernatant, okay? So we're going to do the centrifuge now. The centrifuge should make the solid that formed in here go down to the bottom and the liquid go up to the top because the solid is more dense than the liquid. So to use the centrifuge, we need to have a counterweight. And that counterweight should weigh about the same. So I'm going to add some distilled water into this counterweight. If this solution here were clear, I would want to definitely label these to know which one is which, but you can definitely see a difference in the solution, so there's no need to do that. Here's the centrifuge. There's a test tube in there. We're going to take that test tube out. We don't need that one. And we're going to put these into opposite sides, just like a clock. So the opposite sides, 10 and 4, face them. Notice we don't need lids on them because the force of gravity is downward, the force of the rotation is downward. And I'm going to turn this on. And we're going to run this for a couple of minutes at relatively high speed. And we're going to see what happens during this process. Okay, so picking up on this, now that we've added the ammonium hydroxide, what's going to happen is bismuth hydroxide will be produced, and that is a solid. It's insoluble in water, so it'll precipitate out as a solid. The other ions, the copper and the silver ions, do not form a precipitate with hydroxide, so they'll stay in solution in the water. So by centrifuging it, we are going to separate the bismuth from the copper and the silver. So it's now been running for a couple of minutes, so let's come back over here to the centrifuge. We're going to stop the centrifuge, and we're going to take a look at what is happening. This centrifuge is equipped with a brake, so by holding down this switch, we can slow down the rotation so that it doesn't take 5 minutes for it to stop. We can get it to stop in a few seconds. There we go. All right, now the centrifuge is stopped. We'll open this up and let's take a look at what we've got. Take a look here at this solution. See the blue up there? That blue is called the supernatant. It's a liquid above the solid. That should have copper and silver in it. Down below, this is the precipitate. That should have the bismuth hydroxide, BiOH3, so that's the bismuth has been separated from those two. So you can imagine if we want to analyze this now, I'll put my blank back into there, what we can do is we can just pour off the supernatant into another test tube. Being careful not to get any of that solid into here. So I'm going to do a visual inspection. I don't see any solid particles, so I think I did a decent job. But notice there's still a little bit of liquid in there. So what are we going to do about that liquid? We could try to transfer it over here, but if you take a look, we have a lot of liquid. This is qualitative analysis. We don't need every drop. So what I'm going to do is I'm just going to go ahead and put this aside. And now I'm going to go ahead and take a look at what we'll do with this. Moving on to the next step, what it says is you're going to add 20 drops of distilled water to the precipitate and stir. So what I'm going to do before I actually do that is getting a clean one. I'm going to come over here and I'm going to go ahead and suck off some of that liquid just to make sure that this precipitate is not contaminated by that liquid. Okay? And then I'm going to go ahead and put this aside. So now we have just the solid precipitate. What it says to do is to add 20 drops of distilled water and then to stir it. Now the logic here is that if we add 20 drops of water and there is still copper and silver, a little bit of contamination, we can rinse that contamination out by stirring this. So I'm adding the water, and then what I'm going to do is I'm going to stir it. Mix it up really well. Now you may notice there's a little bit of solid down there at the bottom. So one way we could deal with that is just to keep vortexing it, or we could go back to the old-fashioned way, come back over here to the glass stirring rod, and do a little physical agitation that way. Sometimes the old-fashioned technology is a little faster than the older technology. So now I'll come back over here, and again put it on the opposite side, and we'll centrifuge again for 2 minutes. And in that centrifugation, we should be separating any contaminants, any copper or silver ions into the supernatant, and then the bismuth hydroxide will stay down at the bottom. So 2 minutes, again, 2 minutes of centrifugation. Okay, so now we've done the centrifugation for a couple of minutes. I'm gonna hit the brake here. We'll stop this and we'll see what happened. If we see a blue tint to the solution above, the supernatant, that tells us there's some copper or silver in there. If it looks clear, then that means we've got a pretty pure solution. If you take a look there, it looks pretty good. Looks like a clear solution in there. We have the white solid down at the bottom, so we have a very good separation, and it doesn't look like we have any contamination of copper or silver there. So what I'm gonna do is I'm just gonna get rid of that solution. We don't need that solution. What we need really is the precipitate down at the bottom. So I'll put the blank over here, the counterweight. I'm gonna grab one of these, and just to be on the safe side, if there is any copper or silver, it would be in that liquid. So I'm gonna take that out. Notice I got a little bit of the solid with me, but that's okay because we're gonna treat all of that solid that we have in there, and that's plenty for us to be able to handle. Okay? So now that we've done that, our next step is come over here, and we're gonna add 10 drops of 0.1 molar tin chloride, SnCl2, and 10 drops of 3 molar sodium hydroxide. This will make the solution very basic, and the tin will undergo a reduction oxidation reaction with the bismuth. Here's the equation. The bismuth hydroxide will react with the tin. By adding the sodium hydroxide, that makes it tin hydroxide. They will react in a redox equation to reduce bismuth 3 into bismuth. The tin gets oxidized. Bismuth, a metal, is black when it's ground up into a powder. So if we see a black solid, that tells us that we have bismuth, which means we must have had bismuth hydroxide, which means originally we must have had the bismuth 3 ion. So let's come over here. We're going to take a look at the chemistry. Let's look at this reaction here. What it says is to drop 10 drops of the tin chloride. So here's our tin 2 chloride. 10 drops into the precipitate. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, there's our tin chloride. But we are also going to have to add 10 drops of the 3 molar sodium hydroxide to make it basic. So here's our sodium hydroxide. One, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, now we're going to stir it. Vortex mixer will stir this very nicely. Okay. Notice there's still some solid down there. So again, we can come back to our old technology, mix that in really nicely. Now the next step is to centrifuge it, and if we get a black solid, we know we have our result. Okay, so now we'll stop this centrifuging and we'll see what's going on with the bismuth. If we get a black solid, a black powder down at the bottom, that tells us that we had bismuth in the solution. So let's take a look and see what this is. Take a look there, very nice. See that black solid there on the side? That black solid is indicating that we have metallic bismuth. That means that our known solution has bismuth in it. as we expected. The real test is what's going to happen with our unknown. Will our unknown also have this black solid? So I'm going to come back over here, and I'm going to do exactly the same thing with the unknown. This is the 15 drops. We're going to go ahead and add the ammonium hydroxide. I'm going to add 15 drops of ammonium hydroxide. 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 13, 14. Get one more drop. There we go. Ammonium hydroxide. Once we add the ammonium hydroxide, of course we need to mix it. The vortex mixer will mix this one very nicely. Again, ammonium hydroxide is a base. So if we are adding a base, we definitely want to test the acidity, make sure that this is basic. So taking a drop, if you take a look at that, that pH paper definitely turned green. That means this is sufficiently basic for us to analyze. We come back over here, and we're going to centrifuge this to separate the potential bismuth from the silver and the copper. So we'll set this for 2 minutes. Okay, so we've now done this separation, and this is the first step of analyzing the bismuth, analyzing for bismuth. If bismuth is there, we don't know whether it is. This is the unknown. So we're going to stop the centrifuge and take a look and see what we've got. Now, if you take a look at the test tube, notice there is a little bit of solid down there at the bottom. So there's definitely a precipitate. So we're going to analyze that precipitate. Again, this is the supernatant up here. We're going to pour that off, and we're going to use that in our analysis for copper and silver. So we do want to be careful when we do this separation, because if we get any of the solid into this transfer, that solid can affect the results for our later tests. Notice also that I have labeled this supernatant, so that we know what that is. Okay? A little bit more liquid in there, so I'm going to try to get a few more drops of that liquid. There we go. And there's a tiny bit in there, so what I'm going to do is I'm going to get rid of that tiny bit of liquid, just to reduce the contamination of our potential solid. Okay. And then it says in the next step we want to add 20 drops of distilled water. Actually, I'll go ahead and use this one. This is a pure distilled water sample. That way we don't have to worry about adding any potential contaminants. So 20 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now when you're adding water and it says to add 20 drops, really we're just adding enough to make sure that we can mix this well. So if it's not exactly 20, that's okay. When you're adding reagents, you want to be a little bit more careful. Now we'll go ahead and mix this, the solid in there. What we're doing in this process is we're trying to make sure that that solid doesn't have any contamination. The contaminants for this experiment, in this step, are copper and silver. So we just want to make sure that any copper and silver that's in there goes into the supernatant. So the bismuth should be forming a solid, so it should go down to the bottom as a precipitate. So now we're going to separate this again via centrifugation. Do this just for a couple of minutes, and we'll check and see whether we've got a pure sample. All right, so now we're going to stop this one. Again, we're doing the unknown now, so we're going to see what this solution looks like. We're rinsing the solution to see if there's any copper or silver, and if there is, those two ions will go into the supernatant, and we'll be able just to rinse those off and not have to worry about them. Take a look. Looks pretty clean. I don't see any blue in there, so it looks like it's pretty clean, but the silver ion doesn't really have any color, so we wouldn't be able to tell. So we'll pour this off. There we go. There's a little bit more in there, so I'm going to go ahead and pull that off with a transfer pipette. And we still have solid in here. So now, if you recall with the known, the test is to add the 10 drops of the tin chloride and the 10 drops of sodium hydroxide. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then the 10 drops of sodium hydroxide. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now we come back, we're going to mix this up using the vortex mixer. Okay, again, there's a little bit of solid down at the bottom, so why not take advantage of the glass stirring rod and make sure that that's mixed in well. Now we'll come back, we'll separate, and if we get a black solid at the bottom, that tells us that the unknown also has bismuth. Bismuth 3 ion was the original ion to form that. Okay, so now we have our unknown testing for bismuth. Let's take a look and see if we get our result here. Now, if you were paying attention right before I put this in the centrifuge, you may have a sense of what the result is going to be. There's a little bit of a hint there when we took a look at that solution. So let's take a look. That's our water. See down there? See that solid right there? That black precipitate, that indicates that we have bismuth in our unknown. So guess what? This unknown also has bismuth in it. So I'm going to go ahead and put this right over here. Move over to our result table. The known had ammonium, the unknown had ammonium. Now for bismuth, of course the unknown is going to have it, but we also, the known and the unknown, both have that particular ion. 2 positive tests for our unknown. Now, we're ready to move on to part C, which is the separation and conformation of the silver ion. That's our 3rd ion we're going to test. If you recall, there was a supernatant solution that we were told to keep in part B. We're going to analyze that supernatant now. What we're going to do is we're going to add hydrochloric acid to that particular solution, in this case 10 drops. Now, the chemistry of silver is very specific when it comes to chloride. Silver ions, Ag+, will react with the chloride ion to form a white precipitate. So by adding hydrochloric acid, we're adding chloride to the solution. That chloride can combine with the silver to make a white solid. But what about the copper? What if there's copper in there? Well, it turns out that if you add chloride to the copper, no reaction takes place. The copper is more attracted to water than it is to chloride, so it will stay in solution. So we're going to come back, we're going to add hydrochloric acid to that supernatant solution. Of course, I'm going to go ahead and do the known for this one. Okay? Hydrochloric acid, HCl. We're going to use 6 molar. It's a nice high concentration. This should give us a good source of chloride. It also has the added effect of being pretty reactive. 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, this is an acid. If we're adding an acid to this solution, we want to test the acidity. So I'm going to go ahead and take a glass stirring rod, mix it up, and try our little pH paper. See how it turns red? Red for pH paper is the color of acidic. That means this solution is acidic. If we're adding hydrochloric acid, we want it to be acidic. Once we've got this solution, now we can go ahead and centrifuge out. See the cloudiness in there? When you see cloudiness, that's an indication you may have a solid. So by centrifuging it, that solid can be put down to the bottom. If that is a white solid, there is a very good chance that that's silver chloride. So let's come over here and we'll centrifuge this one for a couple of minutes, and that'll tell us whether we've got silver chloride and hence silver in the solution. Okay, so let's take a look and see whether we can detect the silver chloride precipitate down at the bottom of the test tube. This is the known now, so we would expect it to be there. All 4 ions are in the known. So let's open this up. And that's the water again. You'll notice I'm always picking up the water. Okay, so there we go. There's some solid down there at the bottom. That would be the silver chloride. But taking a look at there's a lot of it on the side. So now what I'm going to do is I'm going to take another test tube and I'm going to pour off that supernatant. And if you take a look at it, there is some solid that got transferred into this test tube. So we don't want that solid to get transferred over from here into there. We want just the supernatant. So how do we deal with that? Well, there's a couple ways we could do it. We could pour the whole thing back in there and recentrifuge it, or we could say, wait a minute, we still have a lot of the solid in here, so that looks pretty good, but maybe we'll just want to clean up the supernatant here and precipitate out the solid there. So we'll try it that way. So I'm going to take this, I'm going to put it back into here, close the lid, and we'll centrifuge this for a couple minutes just to clean that up. Okay. All right, so we're going to clean this up, make sure that that supernatant is clean. We don't want to have any contamination in it. So let's take a look and see how this looks. All right, we'll open this up. And there we go. See, there's a little bit of solid down there. That would actually be the silver chloride. So what I'm going to do, just to be on the careful side, is I'm going to come over here and I'm going to transfer some of that supernatant over into here, making sure that I don't get the solid with it. I just want the supernatant. So there's our supernatant there. Maybe a little bit more. We'll put that over here. There's our supernatant. We're going to use that in the next part. Now, what about this one? Well, this one has a little bit of solid and has a little bit of supernatant. We don't need that though. Again, this is qualitative analysis. So I'm going to go ahead and put that in there. And now, the next step is to take this silver chloride and determine whether it will dissolve by adding ammonium to it. Ammonium hydroxide, that is. Ammonium hydroxide, the ammonia in the ammonium hydroxide can combine with the silver ion, and if it combines with the silver, it'll essentially take it off the chloride and dissolve the solid. So I'm going to go ahead and add ammonium hydroxide to this precipitate. 3, 4, 5, 6, 7, 8, 9, 10. I'm going to add actually a total of 15 drops. 11, 12, 13, 14, 15. There we go. And we're going to see if this dissolves. Let's see. Looks like it's going. Looks like that solid, that precipitate is dissolving. That means that it must have been silver chloride. Silver chloride will dissolve, the precipitate will dissolve if you mix it in ammonium hydroxide. So there we have a confirmation for our known. There was definitely some silver chloride in there, and that means there was definitely silver in our known solution. So we have a positive test for that. Okay. Now, we're going to do the same thing for the unknown. We're going to see if we have silver in there. So again, I'm going to use the hydrochloric acid, 6 molar hydrochloric acid, in order to see if we can precipitate out silver. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There we go. Okay, so now, let me just be a little bit careful here and make sure that we've got a clean stirring rod. So I'll rinse this a little bit. With some distilled water. Wipe her clean. And let's take a look here. Mixing it in there. Now, I added hydrochloric acid. We're going to test to see whether it's really acidic. Is that solution acidic? Well, let me try another drop. There we go. Red. pH paper turned red. That tells us this is definitely acidic. That means we added enough hydrochloric acid. If you take a look at that, however, there's no precipitate. No solid at all, as far as I can tell. What does that tell us? If there's no precipitate, that means there's no silver chloride. If there's no silver chloride, that means there's no silver. So we've got a result now. We have a result which is different from what we just had. For the known, the silver was a positive, as we expected it to be. But for our unknown, we have a negative. That is not a positive test. So we have a difference. This is our first one where we can see an actual difference between two samples in the same ion, which is the sodium. That leads us to the last ion that we're going to analyze for this procedure, and that is the copper 2 ion. So let's come over here. Confirmation of copper 2. There are 2 tests to confirm the presence of copper 2 ions. To the first confirmation test, half the supernatant that you saved from part C, we're going to add 10 drops of 6 molar ammonium hydroxide. If it turns dark blue, that means you got copper 2. To the second confirmation test, the other half of the supernatant, we're going to add 4 drops of 0.1 molar potassium ferrocyanide. We then centrifuge it. If we get a red-purple precipitate, that tells us that there's copper 2 in it. So let's try the first one. Let's come on over here and we will take a look at our supernatant for the known. Okay. So there's our supernatant for the known, but we only need half of it. So I'm going to pour about half of it in here. A little more than half. Let's pour just a tiny bit back. It's an iterative process. Now, one way I could do this a little bit more quickly, is to just go ahead and take one of these transfer pipettes. When you're transferring small volumes in these plastic tubes, sometimes it's difficult to get it to go. So this is just half of the supernatant. So it says to add ammonium hydroxide. And the logic behind this is that ammonia will combine with the copper 2 ion to make a blue complex. So I'm going to add this. Take a look at what's happening. See that blue right there, that dark blue complex? That's a definite positive test. That tells us that we definitely have copper 2 in here. Now we have the other half of the supernatant, and what it says to do with that one is to go ahead and add the potassium ferrocyanide. So we're going to add potassium ferrocyanide. And it says to centrifuge. The presence of a dark red precipitate. Now take a look at that. That's definitely dark red. So we could go ahead and centrifuge this in order to see it. But if you take a look at that, that is definitely dark red. So we've got a positive test there. So both the ammonium hydroxide test and the potassium ferrocyanide test, both of them give us positive results. They should be complementary to each other. Now, what about the supernatant for our unknown? We don't know whether copper's in this one, so I'm going to pour half of this one. Now, actually, maybe I learned from my previous lesson that maybe it's a little easier just to use a transfer pipette. Okay. And now what we're going to do is we're going to add ammonium hydroxide to the first one. And what do we see? Dark blue again, deep blue, beautiful blue color. It's really, the copper 2 ion in ammonia is very beautiful. That blue test really gives us the answer. That tells us that there's definitely copper 2 in our unknown. We actually know that already, but now we could do one more test, which is to add the potassium ferrocyanide, and let's see what happens here. Again, we're expecting a red precipitate. Oh, 1 drop immediately there, right? Here's the known, here's the unknown. 1 drop of the potassium ferrocyanide gave us the positive result. So our unknown has, again, just like the known, 2 positive results. We have the copper 2. So I'm going to come back over here and I'm going to indicate that for our copper 2, we had a positive result in both tests, and for our unknown we had a positive result for both tests as well. So now we've done it. We've gone through this entire procedure with a known and an unknown. We did it side by side so that we could really see the comparison well. Our result is that the known definitely has all 4 ions. The unknown has 3 out of the 4. The only one it didn't have was the silver ion. Now, I do want to talk about one more thing, which is laboratory safety. If you'll notice, during this lecture, I have been wearing gloves, I have been wearing a lab coat, and I've been wearing safety goggles. Safety is probably the most important thing in a chemistry laboratory, more than really in many other sciences, because of the reagents that we're working with. 6 molar hydrochloric acid, 6 molar sodium hydroxide, 6 molar ammonium hydroxide. These are reagents that we want to be very careful with. We want to be careful in terms of how we transfer things. And finally, we also want to be careful about how we deal with the solutions that we've worked with. We've been working with copper, silver, bismuth, ammonium, hydrochloric acid, sodium hydroxide. What do we do with those sorts of materials? In the old days, we would have just rinsed them right down the drain. But over time, we've come to realize that it's more important to deal with them more safely. We don't want to overload our drinking water facilities, our clean water facilities, the water that we use in wherever we live. So I'm going to take all of these solutions and I'm going to rinse these solutions, dump them into this container, and we're going to call this a waste container. And I'm going to take this waste container and I'm going to move over to our room waste container, which is right over here. This room waste container has an orange slip on it. It's indicating what reagents we're adding. That way we know at the college what to do with the solution, how we deal with it. Are we going to put it into one bottle or another? And so I'm going to open this up. I'm going to pour the waste in. And then I'm going to close the container up. And we're also going to note that we're not the only ones that are using this laboratory. Other people will be using this laboratory, so we want to have chemical hygiene for them. So if this glassware is going to be used by another group, we want to rinse this out. We want to make sure that it's clean and doesn't have any contamination in it. So I won't show this on this video, but we would also rinse out all of our glassware. We would make sure that all of the containers that have chemicals in them are capped off. Everything is labeled properly and put away. And any electrical appliances that we're using in the laboratory, such as the hot plate to boil the water, that those would be turned off and unplugged in order to protect everybody who's in this laboratory. So that completes this particular experiment. 2 experiments, the group 1 known and the group 2 known, group 1 unknown. So you'll be doing a little worksheet on this in order to analyze the results and submit that to your instructor.